Hello, everyone. So last time we were looking at slope fields. We saw that how to use slope fields to sketch the graph of a solution of a differential equation without solving it algebraically. So last time we saw about slope fields and how to use them to sketch the graph of a solution of an ODE of the form y prime equals f of x and y. And you also saw about the conditions for uniqueness, existence and uniqueness of solution of a differential equation of this form again. Also saw about existence and uniqueness conditions for solutions or maybe I can say that conditions for existence and uniqueness of solutions of ODEs of the form y prime equals f of x and y. Picard's theorem. Basically, Picard's theorem was saying that if this small f in the right-hand side is continuous, and if also partial derivative of this small f respect to y exists and is continuous at the point x0, y0, remember that the initial condition was y of x0 equals y0. If the partial derivative respect to y is continuous at this point, and the function is continuous, then we can say that the solution for this equation exists and is unique. So let's look at an example. We did one example last time. Let's look at another example. Does the solution of y prime equals 2x plus 3y squared with y of 1 equals 2 exist? And if so, is it unique? So the answer is we have to apply Picard's theorem. Let's apply Picard's theorem. So what is f of x and y here? So here, remember our reference form is an equation of the form y prime equals f of x and y. Now, what is f of x and y here? F of x and y is 2x plus 3y squared. F of x and y equals 2x plus 3y squared. So this function is, of course, continuous everywhere. Because polynomials, it's a polynomial of two variables, but it's a polynomial. So polynomials are always continuous, whether in one variable or two variables, they're always continuous everywhere. Polynomials are continuous everywhere. What about the partial derivative of f respect to y? Does it exist and is it unique? Partial derivative of f respect to y means you have to fix x, behave x as a constant, and differentiate respect to y. So if x is a constant, derivative of 2x will be 0, and derivative of 3y squared respect to y is 6y. So add df to dy is 6y. Again, this one is continuous everywhere. Again, because polynomials are continuous everywhere. Polynomials are continuous everywhere. So by Picard's theorem, we can say that the solution for ODE above exists and is unique. Okay, so please remember that if you want to apply Picard's theorem, you need to check two conditions. The original function, small f in the right-hand side must be continuous. That's one condition. Second condition, derivative of that function respect to y also must exist and be continuous at the point x naught, y naught. Okay, so if both these two conditions are met, then you can apply Picard's theorem. So let's look at another example. So far, all the examples that we did satisfied the conditions given the Picard's theorem. Now let's look at an example where Picard's theorem conditions are not satisfied. So let's look at this example. Consider y prime equals 2 times root absolute value y with y of 0 equals 0. Are the conditions of Picard's theorem satisfied? Is the solution, or does the solution exist? And if so, is it unique? Because these are the questions we want to answer here. All right, so if you want to check the conditions, so in order to check the conditions of the theorem, we need to check continuity of f and continuity of partial derivative of f respect to y at the point 0 and 0, because it says that y of 0 is 0. So in order to check the conditions, we need to check check continuity of f of x and y equals 2 root absolute value y at the point 0 and 0, and also continuity, existence and continuity of again, df to dy at the point 0 and 0 again. So first, note that 2 root absolute value y is continuous at y equals 0. So this one you can check yourself. Basically, the idea is that absolute value y is continuous at y equals 0. Instead of x, we are using y, doesn't matter, right? So in math 113, you saw that absolute value x is continuous at x equals 0. Similarly, absolute value y is continuous at y equals 0. And root x is also continuous everywhere on its domain. So we can use the fact, and this is the composition of root y and absolute value y. And composition of two continuous function is continuous. So that way you can check that this function is continuous, or you can just find use the original definition of continuity. In order to check continuity of a function, you need to calculate left limit and right limit, and also the value of the function at the point. So basically you can check that limit 2 root absolute value y as y goes to 0 minus is same as limit 2 root absolute value y as y goes to 0 plus, and this is same as 2 root absolute value 0, which is 0. So if you check that left limit and right limit and the value of the function at the point are all equal to each other, that means that the function is continuous. So maybe it's easier to check the continuity this way, using the original definition of continuity and checking that left limit, right limit, and the value of the function at the point are all the same. So please check this, that left limit, right limit, and value at the point are all 0. And so first note that this is continuous at y equals 0. Next, we need to check existence first, existence of df to dy at y equals 0. Let me say at x and y equals 0, 0. So how can we do that? So basically df to dy at x and y equals 0, according to the definition, this is basically a math 213 simple exercise in math 213. In case you haven't taken math 213 before, we know that the partial derivative respect to y at a point can be written using the limit definition. Limit definition, you saw the limit definition of derivatives in math 113. This is similar to that. The only thing that you have to be careful about is that when we talk about partial derivative respect to y, that means we are taking x as a constant. So we are fixing x value. Fixing x value to be what? To be 0. Because x is 0 and y is 0 here, right? So we fix x to be 0. So limit f of 0 and, but for y value, we can change it, right? So limit f of 0 and 0 plus h minus f of 0 and 0 divided by h approaches to 0. See, if you compare this with the definition you saw in math 113, in math 113, you had the function of one variable, and then you define this as limit f of a plus h minus f of a divided by h goes to 0, right? So see, this is similar to that. The only difference is that this time we have a function of two variables, but one of them we fixed it because it's partial derivative respect to y. So we fixed the x value to be 0, and we are letting y value change. So fix x value to be 0, this is 0, this is 0, but y value we change it from h, 0 plus h to 0, similar to here, a plus h to a, and then divided by h. All right. So if we continue this, now f of 0, this one can be written as f of 0 and h minus f of 0 and 0 divided by h approaches to 0. And then this one, we can write it as limit, well, what was f of x and y here? F of x and y was 2 root absolute value y. So f of 0 and h will be 2 root absolute value h f of 0 and 0 will be 0 divided by h. H approaches to 0. Now we can do the right limit and left limit separately. So for right limit, limit h approaches to 0 plus 2 root h, right? Because if h goes to 0 plus means h is positive. If h is positive, then absolute value h will be same as h itself. So 2 root h minus 0 divided by h. And this is limit 2 over root h goes to 0 plus. And this is infinity already. And what about the left limit? So this alone shows that limit does not exist, because if one of the one-sided limits is infinity or minus infinity, it already implies that the whole limit does not exist. But just if you're wondering what the left limit would be, so we can say limit h goes to 0 minus. If h is goes to 0 minus means h is negative. If h is negative, root h will be replaced, absolute value h will be replaced by minus h. If h is negative, absolute value h will be same as minus h divided by h. Now we can write this one as basically we can write, because h is negative here, so it's a little bit tricky to handle this one. 2 root minus h, I can write this one as root minus h times root minus h, 1 minus in front. See, you may wonder how come we have root minus h. Many people say we don't have root of a negative number. Root of a negative number is undefined. Well, minus h is not a negative number. That's the thing. That's the point. Because h itself is negative, so minus h is positive. So I don't have root of a negative number here. It's root of a positive number. Root minus h times root minus h. This is under the square root, is a positive number. Under the square root, this is also a positive number. This will be minus h, 1 minus in front. That will give me h. And 2 root minus h, I just wrote it, what we had before. Now I can cancel this guy with this guy. So this will be limit 2 over minus root minus h goes to 0 minus. This will be 2 over minus 0 plus, right? Because if h goes to 0 minus, minus h will go to 0 plus. Root 0 plus is 0 plus, but there is a 1 minus in front. 2 over minus 0 plus. This will be 2 over 0 minus, which is minus infinity. So right limit will be infinity, left limit minus infinity. So we can say that limit f of 0 and h minus f of 0 and 0 divided by h goes to 0 does not exist, meaning that df to dy at 0 and 0 does not exist. So that means Picard's theorem cannot be applied. Because the conditions of Picard's theorem were not satisfied, so Picard's theorem cannot be applied. Now, the second part of the question was asking whether we have a solution, and if so, whether the solution is unique or not. But we do have a solution here. What is the solution? Well, let's look at the equation again. See, it's y prime equals root 2 absolute value y. Now let's try y equals 0, because especially the initial condition is y of 0 equals 0. So why don't we try y equals 0 as a solution? So if y is 0, we have more than one solution for the given equation. So guess number one, y equals 0 is a solution because y prime will be 0 and 2 root absolute value y will be 2 root 0, which is 0. So y prime will be same as 2 root absolute value y. And obviously y equals 0 satisfies y of 0 equals 0. So that means, okay, it seems that the screen is freeze. Let me see. Okay, so I was saying that we have more than one solution for this equation. Our first case is y equals 0. So that means constant function 0. Constant function 0 is a solution for this equation. Why? Because when you consider constant function 0, derivative of constant function 0, of course, is 0. And 2 root absolute value y, if y is 0, it will be 2 root 0, which is also 0. So in this case, if y equals 0, y prime will be equal to 2 root absolute value y. So the ODE is satisfied. The initial condition is also satisfied because when you have y equals 0, that means constant function 0 is 0 everywhere. So y of 0 is 0 in particular. And therefore, that's one solution. Now, our second guess for this equation, let's look at it. It's a little bit hard to come up with a second guess. Well, if it's hard to guess in the exam, it's possible that I give you the guess and ask you to verify that this is actually a solution. So it's a little bit hard to guess the second solution, but you can also try to see whether you can come up with this solution without guessing. So guess number 2. Y equals x squared if x bigger than equal to 0 minus x squared if x less than 0. Okay, so you may try to find this solution without guessing. But right now we want to basically proceed based on guessing this solution. So like I said, I agree that it's hard to guess this solution, but if it's in the exam, if it's something if you need to use some function that is hard to guess, I will give you the guess, and then I will ask you to verify that this guess is actually a solution. So we want to see whether this is a solution. Let's verify that this is a solution. For our ODE. Okay, so maybe I can mention here that it's tricky to come up with this guess. In the exam, it will be given. Okay, only the function will be given, but the rest, that is, verifying that this is a solution, will not be given. You will be required to do that step. So how can we verify that this is the solution for our ODE? We need to verify two things, that y prime is equal to 2 times root absolute value y, and need to verify that y of 0 is 0, because remember our original ODE had one initial condition. The equation was y prime equals 2 root absolute value y. Initial condition y of 0 equals 0. But y of 0 equals 0 is obvious, right? This is your y. How much is y of 0? That means replace x with 0. Well, it's a piecewise function. For x bigger than or equal to 0, we have to use first formula. For x less than 0, we have to use second formula. So if x is equal to 0, we have to use the first formula. And then we will have, if we use the first formula and replace x with 0, the value of y will be 0 squared, which is 0. So this is obvious based on the formula for y. Now let's verify y prime equals 2 root absolute value y. We need to also verify this equation. We need to verify that this equation holds. All right, so we need to first calculate y prime. To calculate y prime, so what will be y prime? Y prime means dy to dx, means d to dx of this function here, which was x squared if x bigger than or equal to 0, minus x squared if x is less than 0. Now, if you want to differentiate this function for x bigger than 0, we need to calculate d to dx of x squared, right? This is a piecewise function. For x bigger than 0, we need to use this formula, and derivative of this formula is 2x. For x less than 0, and then we need to find d to dx of minus x squared, which is minus 2x. And for x equals 0, we have to do it separately. Many students make a mistake here, and they think because this formula is for x bigger than or equal to 0, then for x equals 0, we can use this formula to differentiate, and derivative of 2x at 0 is 0. That's not a correct approach, because derivative at the point depends on the behavior of the function, both from right side of that point and also left side of the point. So if you want to find derivative at the point, the value, it's like limits, right? Limits, when you calculate limit of a function, the value of a function at the point A is not important. The value of the function right to the A and left to the A are important, right limit and left limit. Derivative is also a special type of limit. So derivative at a point depends on the behavior of the function, the formula for the function, to the right of that point and to the left of the point, and also at the point as well. So my point is, you cannot say that because the formula for x bigger than or equal to 0 is this, so you cannot say therefore for derivative at 0 we have to use this formula. The formula of the function left to the point of 0 is also important, which is this. So if I, let's say, keep the formula at 0 to be this, but let's say if I change the formula to the left of the point, let's say minus x squared minus 1, then the function is not even differentiable at 0. Right? So right now that we don't have this minus 1 here, I will show you that the function is differentiable at 0, and I will find the derivative at 0. But I want to emphasize that derivative at 0 depends on the behavior and the formula for the function, both to the right of the point and left of the point and at the point. And to justify my statement, I'm saying that if, let's say, I keep the formula for the point 0 and right of the point to be same, but only change the formula to the left of the point to be minus x squared minus 1, rather than just minus x squared, then the function will not be differentiable at 0 anymore. Why? Because this function is not even continuous at 0. Right limit is 0, at 0 is 0, left limit at 0 is minus 1. It's not even continuous, and if a function is not continuous, for sure will be not differentiable. Okay, so please do not make the mistake saying that because the formula at 0 is this, so I will use this formula to find derivative at 0. To find the formula derivative at 0, you need everything together at the same time. The value at 0, the function or the formula to the right of 0, and the formula to the left of 0. So for x equals 0, we need to evaluate limit, let's call it, I call it y. So y of x minus y of 0 divided by x. X approaches to 0. So we need right limit and left limit. For right limit, limit y of x minus y of 0 divided by x. X approaches to 0 plus. So this will be limit x squared minus 0 divided by x. X goes to 0 plus. That's limit x. X approaches to 0 plus, which is 0. For left limit, limit y of x minus y of 0 divided by x. X approaches to 0 minus. This is limit minus x squared minus 0 divided by x. X approaches to 0 minus. This is limit minus x. X approaches to 0 minus. This is also 0. So that means, let's call this one limit star. So limit star above exists and is 0. So y prime of 0, or y prime at x equals 0, or we can say y prime of 0, which is same as y prime at x equals 0. This is 0. So we can say that y prime, if x is positive, see, if x is positive, y prime will be 2x. If x negative, minus 2x. At 0, it's 0. So y prime equals 2x. If x is positive, minus 2x. If x is negative, 0 if x is 0. And combining this, we can also write this one as 2x if x bigger than or equal to 0, minus 2x if x less than 0. So our final answer is same as the answer that with answer of the students making the mistake, saying that, well, the formula for y, for x bigger than or equal to 0, x squared, so the derivative is 2x. For x less than 0 is minus x squared, so the derivative is minus 2x. So our final answer is same as the final answer of those students, but those students will get just a little bit points because their process is wrong. So that's why in math, final answer worth very little points. The most points are for the process, for the steps, and for the justification. Okay, so it's very important how you justify this final answer. All right, what about, so this is for y prime. What about the right-hand side of the equation above? So root y for absolute value y. First, let's calculate absolute value y. This is absolute value of this function, x squared if x bigger than or equal to 0, minus x squared if x less than 0. Okay, absolute value of this function. And we can write this one as absolute value x squared if x bigger than equal to 0, absolute value minus x squared if x less than 0. Absolute value x squared according to absolute value properties is same as x squared. And absolute value minus x squared is also x squared. These are absolute value properties. Because absolute value, because x squared is always already non-negative, so absolute value x squared is x squared. Absolute value minus x squared is also x squared. So this one for x bigger than equal to 0 and x squared if x less than 0, which we can write it as x squared because for every x value, the output is x squared, whether x positive or 0 or negative. So I can say that the output is always x squared, no matter what x is. So I can write this function as simply x squared. And then, so this is absolute value y. So 2 root absolute value y will be how much? 2 root absolute value y was x squared. So this one we can write it as 2 root x squared is absolute value x. Root x squared equals absolute value x. This one also you learned in pre-calculus. And therefore we can write this one as 2x if x bigger than equal to 0 and minus 2x if x less than 0. Absolute value x, according to the definition of absolute value x is equal to x if x bigger than equal to 0 and minus x if x less than 0. So let me call this one equation 3 star. And let me call this equation here equation 2 star. Comparing equations 2 star and 3 star above, we can conclude that y prime is equal to 2 root absolute value y, or y equals x squared if x bigger than equal to 0 minus x squared if x less than 0. So y prime is equal to, so that means this is also a solution. So we found two different solutions for y prime equals y prime equals 2 root absolute value y with y of 0 equals 0. So one solution for this equation, we saw that our first guess was y equals 0. Y equals 0 obviously satisfies this and also satisfies this. Our second guess, which was tricky to come up with that guess, is this function. And this function obviously satisfies this condition. It was a little bit harder to show that it satisfies this condition as well. But with some calculation, we showed that it satisfies this condition as well. So that means we found two different solutions for this equation. So it's a first order differential equation with one initial condition, but it has two different solutions. Is that okay? That's okay. You know, there's doesn't contradict Picard's theorem, because Picard's theorem guarantees unique existence and uniqueness of the solution only if this function in the right-hand side is continuous at the point, which was continuous in this case, and also it required the partial derivative of this function with respect to y to exist and to be continuous at this point. However, the partial derivative of this function respect to y did not exist at 0. So it did not contradict Picard's theorem, the fact that this equation has two different solutions. Okay, guys.